Great. So thank you for coming. This is actually the work of Arindam Day, and he couldn't come here today, so I'm presenting on his behalf. I was the third author, but him and Alex did most of the work. And this is actually in the context of training. So of course, we're very familiar with lots of examples of virtual reality training. This is a training simulator for helicopter pilots to train how to drop the helicopter hoist down. And in many VR training systems, they oftentimes have adaptive training where they change the training task based on the user's performance or test performance or some sort of subjective measures. But it's very unusual to have a training task that measures mental activity while the person's training and gives feedback based on that. And so that's what we want to do with this work here. So an example of how you might do that, this is a desktop system called Mentor, where they took an EEG system to measure people's brain activity, and they combine it with an intelligent tutoring system to teach people reverse Polish notation. So those people who are old in the room will remember reverse Polish notation for doing formulas, and it's quite tricky to learn how to use. So they basically built a system like this that would monitor the person's cognitive load using EEG, and if the workload was kind of normal, then they would assume the person was understanding what was going on. They'd ask them a question. If the workload was getting high, they assumed the people didn't know what was going on. They'd provide more examples or more training. And they found when they did this, and when they tested with the group with and without the EEG feedback, then the group that had the feedback were able to achieve higher test scores and also enjoyed using the system more. So this is an example of how you can combine EEG with an intelligent tutoring system on a desktop to provide real-time feedback and training. But nobody had done this type of work for virtual reality. So what we want to explore is, can we make virtual reality systems adaptive in real time to the trainer's cognitive load to produce the best type of performance gain. The motivation kind of was, if you're trying to learn how to do a task, if the task is too easy, you don't really learn. If the task is too difficult, you kind of give up. And you really want to have a training scenario that is challenging but not too challenging. So the idea was that we could use EEG to try and pitch the level of the training to be challenging enough. There's some previous examples of EEG with VR. So on the left here is Friedman's work using EEG for locomotion. So you put the the brain cap on, and you can concentrate and start moving through the environment. So there are many people, including Anatole, who spoke this morning, about how you could use EEG for brain-computer input. This is another project, Zhang, who did a driving simulator, and he would have people driving and wearing EEG, but in this case, they did not analyze the data till after the person had finished the driving task, and there wasn't any dynamic feedback. And on the end, Linda Jerry's project, this is actually a project from our lab that was basically a beta version of what we're trying to build. In this case, we didn't change the task complexity, and we didn't do any user study as well. So the kind of summary is that you can have effective VR training tools. There's been some use of EEG in VR studies, but we think we're the first to build a real-time adaptive VR system that uses workload from the EEG to adapt the training environment. So this is the system we put together. There's a person wearing a Vive with a brain cap on. We only use 6 electrodes out of the brain cap, so this is a brain product system, so a very accurate system. We combine that with the OpenVibe software, which Anatole mentioned this morning, that allows you to process the EEG data and put that into Unity, and then had feedback from Unity when the person was in the training environment. And what we need to do in this case is measure, when people start using the system, measure people's innate cognitive load ability. So we use what's called an end-back task, which is where you recall numbers that were either 1 or 2 before the current number. So it's a typical task used in psychology to establish cognitive load. And so we can then measure alpha activity, and we can calculate the mean of these 2 tasks to establish a baseline. Then the idea was, when people were in the VR environment, you would also measure their alpha power activity. And if their cognitive load was lower than their baseline, you would increase the complexity of the task. If the cognitive load got above the baseline, you would decrease the complexity of the task to try and keep them at that baseline. So here's the experimental task. It was a target discrimination task. So the idea was, you're in a VR environment. In the pink box over there, you see a target. So in the first one, it's a yellow sphere. And then the idea was to look around the VR environment to try and find a yellow sphere, and then pull the trigger on your controller when the sphere is, when your crosshair is covering the sphere. But over time, we increased the complexity. So you started out with 3 or 4 distracting objects, and then you got more and more and more. And by the end, you had 30 or 40 objects that were all moving around, different sizes, and hiding and obscuring one another. So it became more and more complicated to do the task. So I'll show a video of this. This is the very low complexity task. You see he's got to find the green ball. Here's the green ball there. Blue, so very easy. And just looking around and trying to find and click on the objects when you see. And then on the right hand side, this is a more complex task. If I can start that up. So now he's got to click on all the red balls. There are multiple red balls, and some of them are moving, and some of them behind other objects. Now it's the yellow cube. So you can see there's one up there, which was quite hard to find. So it becomes more and more complex. So as you increase the complexity, you'd expect the performance time to change, and also to get more cognitive load. So we did a study with 14 people, and we measured the response time and also the alpha power of the brain activity. And we gave people 5 minutes in the experience, and then we increased the complexity over time. So this is what it looked like for the increasing complexity. As I said, there's a time across here. This is the alpha power measure on the side here. And previously, before people went into the VR, we measured their baseline ability. So this is potentially for one subject. This shows where the baseline is. And then as we started off the trials, we started off with 3 distractors, and we go up to 9. And you can see the measured cognitive load would slowly start increasing. And then until you get to the point where the cognitive load reaches the baseline capacity. And then when you get above this, then as you increase more and more distractors, the cognitive load got above. And so then we started decreasing, increasing and decreasing to try and keep it at that baseline ability. So you can see that gets to 19, and the load is quite far above. So then we decrease it back down to 18, it gets down there. So this is just a hypothetical showing you what the typical would be like, but each person, of course, had their own baseline, and each person was able to perform differently in the task. So these are the results we found. First of all, although there was decreasing on the graph here, there was no significant difference between the easiest and hard levels in terms of the time performance. This is the average number of seconds it took to find the targets. This is the increasing levels. So 1 was had 5 distractors, 2 had 10, and 3 had 20, and they were all moving around, so it's more complicated. So no significant difference in performance time, but we also measured the time frequency representation of the brain activity. So on the bottom there is the time, so it shows you how many seconds after the start of the trial or the onset of the presentation of a target the person started responding, and on the y-axis is the frequency. And we were looking at the alpha power, which is between 9 and 13 hertz. So you can see this is at the easiest level. It's relatively low level brain activity. The hardest level is quite a lot of activity, especially, I don't have a pointer, but especially in the 10 hertz and like 0.6 range there. So what we found was that we were getting significant differences in the amount of brain activity, even though the performance time was staying the same. So that was the key finding, that we have a similar reaction time, but we're able to increase brain activity and people had to think or work harder to achieve the same level of performance. So there's some limitations with those. So first of all, this is a very artificial task. It would be better to make it similar to a real-world task, like have people driving a vehicle or shooting a weapon or doing, performing surgery. Also, the difficulty levels, because we weren't getting a performance drop, it probably showed us that the highest levels we have of difficulty weren't difficult enough. So we probably should have increased the number of distractors from 20 to 40 or something. And we only considered alpha activity. We ignored other brain activity. And we also only had 6 electrodes. So we had 3 on each side of the head we're looking at. With the brain cap we had, it's a 32 electrode system. We could have had more brain activity measured, but we didn't pick that. So just to wrap up, what we've shown with this is that we can use an adaptive VR training to increase people's cognitive load. And so after each short trial, we changed the training complexity based on their feedback. So that was able to maintain a high cognitive load. And we also completed the first demo of using the real-time signals to produce more complexity. But there's a lot of more work we can do in this space. So as I said before, we could increase the task complexity. And also, based on people's measured baseline cognitive capacity, we could also predict their performance. There might be some people that come in that perform very, very well on the NBAC task, and we might be able to use that to predict that they'll actually be able to be much better on this targeting task. Also, we are now working on doing this in AR, and augmented reality is very interesting because not only do you have the virtual objects, but you've got the real world you can see as well. And so you can have distractors in the real world, and there can also be visual conflicts between the virtual objects and the distractors. And then finally, it's quite difficult actually to wear an EEG cap on your head, and we had a gel system, so we had to put people in gel and then put the headset on top of that, and all the VR straps are all getting in the way. So there are now some new VR displays that have EEG integrated into them. So this is the neurable system. It has 6 electrodes at the back in the visual cortex. You can see the big blue boxes there, or cylinders. And then we also have a lucid system, which is the one on the right, that has 6 electrodes in the frontal lobe. And so you can buy these now and use them as well. And I think you'll see over the coming years more and more companies starting to integrate EEG and other physiological sensors into the headset displays themselves. So that's pretty much what we've did. As I said, this is Arindam's work, so there's a lot more in the paper you should read about. Arindam also wanted to make sure, he's moved now from the University of South Australia to the University of Queensland, and he's got a few fully funded PhD positions available. So if any of you are students and interested in doing this type of research, combining EEG with VR and AR, then please contact Arindam, and he would love to have you as a student. So thank you very much for your time. I think I've got a few minutes for questions.
Hi, thanks for the talk. Farba Mustajra from University of Hamburg. I just wanted to know why did you use O2 and O1 and P1 and P2 these channels, and so what was your reason for choosing this channel?
Sure.
And the second question about the EEG map. You're relating this image to the cognitive load, but I don't know if I'm correct or not, but I see more activities in the visual cortex. Is it correct, or
yes.
Is it the more activity? So it's just like when you have more objects around you in the difficult task, so you see more objects, more visual information, so you see more information in the visual cortex. But if you're measuring the cognitive load from the other sides of the brain,
yes.
You can't really relate that, so you can't really. I don't know if it's this conclusion is correct. That
So we cheated, and what we did is we took the 6 electrodes we measured. We averaged the alpha power across all of them as well. We wanted the reason why we put them on the side is because with the VR headset we were wearing, we had to actually remove some of the electrodes from around the back and around the top to get the headset to work. So it's just kind of a limitation of the headset design we had as well.
Okay, but this is also correct that different regions are related to different activities. For example,
Yes.
temporal lobe is also related to the math performance. So this
Yes.
is correct, but this is like I didn't understand what was the task completely. But I think the images are on the visual cortex and not even in the temporal lobe. So I mean, you say brain activity is higher in the difficult task, but it doesn't really say that this is more cognitive load for the patient. So look for the participant, and then you say the different cognitive load. I mean, could you go to the last slide for the conclusion? So adaptive VR training can increase the user's cognitive load without affecting the task performance. I think that might not be correct.
Well, I have to punt on that because I wasn't the person that did all the experimental work. So I think you should contact Arindam and ask him. I'm also not a cognitive neuroscientist as well. So Arindam, and then especially Alex, who was the other author on the paper. Alex is a neuroscientist, and so he was one that did the design in terms of the EEG placement and the analysis of the data as well. So,
thank you very much.
But he assured me that having those electrodes was perfectly fine. So. But I'm not an expert in that area.
Thank you.
Thanks for the interesting talk. I've got a similar question regarding the alpha power.
Great.
So in my small world, alpha power usually is like relaxation. When people tend to fall asleep or are very relaxed, then I tend to see alpha power on the back of the heads in my lab. So did you measure in the inverse?
There's a reference in the paper. I don't have the paper here, but it talks about how. In fact, I do have the paper here that correlates alpha power with, it's cognitive load. So I would suggest you read, I can show you the reference in the paper and you can see this, I was just reading it before, this reference right here. Talks about alpha power synchronized retention. And so there's a couple more in that paragraph as well. So
Yeah,
it certainly relates to relaxation as well, but there's also some work showing alpha power relating to cognitive load and attention.
But you didn't use the inverse, like decreasing alpha power might be more activity in the brain.
No, we didn't do that.
Okay.
But
And the other question would be, as you already mentioned, you had problems strapping
yes.
the head holder above the electrodes. And this is exactly what I experienced, especially for the occipital electrodes. So signal quality actually was decreased because the people were moving their heads and just pushing the electrodes around and exerting strain. Did you use sponges, or what was your countermeasure to make it better?
So we had the EEG system we're using was a very high quality system. Plus it was a gel electrode, so we were able to have a wet system. So it was had quite good signal to noise ratio in that sense.
Mm-hmm.
We also designed the task so the people only had to move their head a few degrees on each side. So from the video, maybe not so clear, but basically plus or minus 40 degrees was
Okay.
enough to see. So they weren't turning the whole body around, and I believe they did the task seated as well. I can't remember. So it was basically just turning the head plus or minus, well, probably 30 degrees, I guess, and then just clicking the button. So we tried to minimise motion as well.
Not too much
No.
head
So
movements.
all the targets are in the front. So yeah.
And did you have any modifications to the headset, or just strapping it over?
No, well, we had to take electrodes off the cap, but the headset itself, we just used the basic Vive headset. But we had to take quite a few electrodes off to be able to fit the straps in, which is what's really exciting about these new headsets coming on the market. And
Absolutely.
Although, unfortunately, the Neurable only has 6 on the back with the visual cortex, so there's a lot of stuff happening on the front and top as well, which they don't have. So yeah.
All right. Thank you so
Okay.
much.
Thank you. So, you have a question at the back there as well?
Yes, Mark. Thanks for the nice talk and compliments for taking this challenge, because having EEG and virtual reality is a really challenging task. So you are pioneering this approach quite a lot. And therefore, my question is, if you are using this for virtual reality, of course you show one participant baseline level, but if you have you done in the lab comparisons with more participants doing this task, increasing the cognitive load, and comparing with and without virtual reality, and to see whether there is difference in the EEG distribution?
Sure. So of course we measured baseline for all of the people, so each person individually, just to be clear. But we haven't done a task with them without the VR. But we did the in-back task, of course, with no VR to measure the baseline, and then we did the VR task. But we didn't compare the VR to a non-equivalent task. We have some studies starting on that now, actually, though. So
Yeah, I think this would be really quite interesting to see whether the difference comes from whether it is the cognitive load or the use of virtual reality, whether different brain regions are
Sure.
included in, and how is the temporal resolution also with the task. But really compliments for
Right.
challenging
Well,
this
it's a lot of work still to do, so thank you. But definitely, please contact Arindam if you have more questions and read more information in the paper. So there we go.
Thank you. I think we have
Sorry for that. Yeah.
Okay.